So let us start with the solution of questions of the uh, theory of computation (TOC) of the practice set, practice question paper set. So the first question says that define the finite state machine, abbreviation is FSM. Define the finite state machine with its block diagram. So a finite state machine is a mathematical model used to design the sequential logic circuits, and it consists of a finite number of states. Transitions between those states based on inputs and outputs determined by the current state and or inputs. The block diagram shows how inputs and the present state determine the next state and outputs. So this is the block diagram. As you can see, when we apply an input uh, to the next state logic, then we go to the next state, that is the state memory, and next state logic and state memory are the present states, and finally we apply the present state to the output logic to get the desired output. So finite state machine is a computational model that can be in exactly one of a finite number of states at any given time. It transitions between states based on inputs and produces outputs accordingly. Key components are: first component is input, that is is input is an external signal or data that influence state transitions. Second component is next state logic, which determines the next state based on the current state and the inputs. That is, when we apply some input to the current state, we get the next state. Third component is the state memory, that is represented by flip-flops, and the memory stores the present state updated on each clock cycle. Fourth component is the output logic, that is generates outputs. Output logic generates outputs based on the present state, that is the Moore machine, or the present state plus inputs, that is the Mealy machine. Fifth component is the clock, which synchronizes state transitions. There are two types of finite state machine. One is Moore machine, second is Mealy machine. In Moore machine, output depends only on the current state. In Mealy machine, output depends on both current state and the input. This is the block diagram which I have already explained. So how it works: inputs and the present state are fed into the next state logic. The clock updates the state memory to store the new state. The output logic generates the system's output based on the present state and possibly the inputs. As I have said earlier, that is the distinction between Mealy and Moore machine. This model is widely used in digital electronics, automata theory, and computer architecture for designing controllers, communication protocols, and sequential circuits. So now we jump to second question. Design a automata which accept the entire set of strings over sigma equal to a comma b. So these are the input symbols A and B, ending with the string ABA. So we have to design the automata for this. So we need to design a finite automata that accepts all the strings ending in ABA, right? Ending in ABA. Step one is the set of input alphabet is A comma B, A and B, that is, and we required those patterns which end with ABA. The automata should accept any string that ends with ABA. Example includes because ABA, AABA, BB, ABA, AAA, BA, 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 BA. So all these strings are ending with ABA, as you can see. Step 3 is about the states. So we define states based on how much of the pattern ABA has been matched so far. So state meaning Q0 is the start state. Q1 last symbol was A. That is, we have to recognize the strings ending with ABA. So first we'll take A, then we add B to it, then we add A to it. So ending with ABA. So in Q0, we will be in the starting state. When we reach to the state Q1, last symbol was A. When we reach state Q2, last two symbols were AB. When we reach Q3, the last three symbols were ABA. So the AB, that Q3 will be the accepting or final state. So you can easily draw the transitions as I have explained. This is the transition table. So when current state is Q0, we apply input A to it, and the next state we go to is Q1. And when we apply B on state Q0, that is on the starting state, we get the same state Q0, and so on and so forth. You know how to apply the transitions. And based on this transition table, you can draw the transition table like this. As you can see, Q0 is the initial state marked with an arrow sign. Q3 is the final state because it is double circled. And this is sorry, this is misinterpreted. It is usually the output. OTPUT is not the correct word. It will be OUTPUT. So we get the desired output. As you can see, when we apply symbol, B on Q0, we get Q1. When we apply uh, Q, we get Q0. Okay, and then we get Q1. Q0A Q1. Okay, so this will be. Let me correct it. Let me correct it. So I need to open. Let me open board. Open board. Give me a few seconds. I will correct the state transition diagram. Let me see where is the open board. Let me open from here. Okay, open board. So uh, mm, okay. Now let me correct it. Mm, give me few seconds. Alt tab. Yes. So uh, let us see. So this is not symbol B. This will be A, right? And when we apply the symbol B, we get the same starting state, right? So as you can see from the uh, let me close this open board. Okay. Sorry. So you can correct this diagram as I have explained earlier to you. That is when we apply the symbol A here in place of B, there should be A, and here when we apply symbol, so when we apply symbol A on state Q0, we get Q1, and when we apply B on Q0, we get Q0, right? So as you can see the transition diagram, rest of the transition diagram is okay. When we apply A on Q1, when we apply A on Q1, we get Q1. Okay. I have to correct all the. I have to correct the transition diagram. Desktop. So let me correct the transition diagram for you. So when we apply B on state Q0, we get the same state Q0. When we apply A on Q0, we get the next state Q1, right? So where there is the mistake, you can get it rectified or corrected at your own by seeing this transition table, right? So you can refer to this transition table. Let me explain this transition table to you again. When we apply A on Q0, we get next state Q1. When we apply B on Q0, we get next state Q0. When we apply A on Q1, we get the same state Q1. When we apply B on Q1, we get the next state Q2. When we apply A to Q2, next state is Q3. When we apply B to Q2, next state is Q0. When we apply A on Q3, we next state is Q1. When we apply B on Q3, next state is Q2. So as per this transition table, you can correct this transition diagram. The half of the transition diagram is okay, but half of the transitions are not shown completely in this transition diagram. You can do at your own by referring to this transition table. This is the transition table, right? So you can get so as you can see, this is the final state. Q3 is the final state because it is marked by the double circle, and you can check when we reach the state Q3 from state Q0, all the strings will be ending with ABA, which has been asked in the question, right? So this is the summary. Final state is Q3, right? And this has been explained When we apply A on Q0, we get Q1. When we apply B on Q0, we get the same state Q0. So whatever we have already seen in the transition table, that has been explained for you for your convenience here. You can see and refer to the same transition table to correct the transition diagram, right? All these steps are okay, right? So we have successfully solved the question number 2. Now let us jump to question number 3. Explain the difference between DFA and NFA with example automata for each. So basically there is a one major difference between DFA and NFA. Perhaps as I could remember, when we apply some input symbol to a state, in DFA, we get only one output state. But in NFA, when we apply some input symbol to some state, we can have more than two output or more than two next states, right? So this is the basic difference between DFA and NFA. Let me explain for you. DFA stands for deterministic finite automata. For every state, so it has been written here. What I have explained to you, the same. This is the same difference I have told you. That is, for every state and input symbol, there is exactly one transition to a next state. But in case of non-deterministic NFA or non-deterministic finite automata, for a given state and input symbol, there can be multiple next states or multiple transitions or none. So this is the major difference, right? So in DFA, the machine's behavior is predictable. That is, there is one path per input. In DFA, a string is accepted if it leads to the final state uniquely. Example of DFA is DFA that accepts string containing AB. Example, sorry, in non-deterministic finite automata (NFA), the machine can guess the path. Multiple possible routes can be there. In NFA, string is accepted if any path leads to a final state. Example of NFA is NFA that accepts strings containing AB. So this is the comparison table between DFA and NFA. As far as transitions per state is concerned, in DFA there is exactly one per input, but in NFA, there can be multiple or none per input. As I have explained, this is the major difference between DFA and NFA. Next, as far as epsilon transitions are concerned, in DFA, epsilon transitions are not allowed. In NFA, these are allowed. In DFA, path to final state is unique. In NFA, there can be multiple possible paths to the final state. As far as implementation is concerned, implementation of DFA is easier. Implementation of NFA is harder. As far as expressive power is concerned, the power of the DFA and NFA is same. That is, NFA can be translated into DFA, and same is applicable in case of NFA. That is, we can get the NFA from DFA. So Q0 is the start state, Q2 is the final state. Each input has one defined transition. Epsilon transition allows moving to Q2 without consuming input. Multiple paths possible for the same input sequence. This is the summary between for the difference between DFA and NFA. DFA is deterministic, single path. There are no epsilon transitions allowed in DFA. NFA is non-deterministic. There can be multiple paths. Epsilon transitions are allowed in NFA. And both DFA and NFA accept the same class of languages. That is, both accept the regular language. Now we move to question number 4. Define the finite automata with its tuple. So a finite automata is a 5 tuple. So there are 5 components. Q is the finite set of states. Sigma is the set of input alphabet. Delta is the transition function. Q0 is the starting or initial state. F is the final state. So as you can see, Q is a set of finite states. That is, it can have any number of states, Q1, Q0, Q1, Q2, Q3, and so on and so forth. Sigma is the set of input alphabet. A and B are input alphabets. Delta is a transition function. That is, when we apply some input alphabet sigma to some input state, we get the next state. So this is the delta is the transition function. That is, we take a transition from one input to the next state by applying some input alphabet. Then Q0 is the starting or initial state. That is a subset of finite set of states, capital Q. And F is the set of final states. It can contain more than one state as the final state. That is the subset of the finite set of state, capital Q. So F is the set of accepting state. Accepting state is also known as final state, right? So this is the definition of finite automata. Finite automata is a Mathematical model of computation used to represent and manipulate regular languages. It consists of a finite number of states and transitions between those states based on the input symbols. That is, when we apply some input symbol on a particular state, we get the next state. It is a finite automata is a 5-tuple, as I have already explained to you. So this has been explained repeatedly. The same I have already explained, right? This I have already explained. Now see the example of finite automata. Let us define a simple finite automata that accepts strings ending with A over input alphabet. A and B are input symbols. M is a finite automata. So the first component is the capital Q, that is the set of finite state. There are two states in this example, Q0, Q1. A and B are input symbols. Delta is a transition function. Q0 is the starting state or initial state, and there is only one final state in this example, that is Q1, right? So this is the transition diagram which I have already explained how to. This is the transition table which I have already explained to you how it works. Transition table. For example, when we apply some input A to state Q0, we get next state output state as Q1. When we apply B on Q0, we get the same next state Q0 output state. When we apply A input symbol on state Q1, we get the same state Q1 as the next state. When we apply B on state Q1, we get the next state as Q0, right? So Q0 is the starting state, Q1 is the final or accepting state. So this is the transition table which accept all string ending with A. You can also draw the transition diagram at your own. Now we jump to next question, that is question number 5, which says that design a automata which accept the entire set of strings over sigma, that is set of input alphabet. A and B are input symbols ending with BBA. So as you can see, this is the automata which uh, should end with BBA. 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 B. Just a minute. BBA. So when we start from initial state Q0, when we start from initial state Q0, BBA, BA. So I think this transition diagram is not okay. Let me see. So these are the pattern of strings. So in all these of strings, we can see these are the strings which end with BBA. As you can see, this is also ending with BBA. This is ending with this BBA. Sorry, ending with that ends with BBA. So this is not correct because it is not ending with BBA. This is ending with BBA. This is okay. This is also not correct. This is not correct. Let me highlight it as red. Let me see the color. Highlight. So let me draw which are not correct. So you have to exclude this because these are not ending with BBA. This is also not correct, right? So this is also ending with BBA. This is also ending with BBA. So let me take the green to identify those strings that are ending with correctly with BBA. So this is also ending with BBA. This is also ending with BBA. Now, based on this set of patterns of strings, you have to draw the transition diagram, right? So step 3, Q0 is always the starting or initial state. Q1 is the last symbol. Q1. So when we start from initial state Q0, and when we apply the symbol B, we get the next state as Q1. Then again we apply B, so we get BB. Next state is Q2. That is, we take the transition from state Q1 to Q2. Now when we apply A onto state Q2, we get the next state Q3, and we again we finally get the string BB, right? So we now have got the idea how to draw the transition table. So this is the correct transition table, right? This is the correct transition table based on which you can correct this transition diagram at your own, right? So this transition diagram is not okay. Let me correct it. This transition diagram is not okay. You can draw the correct transition diagram based on this transition table, right? So you can draw the transition diagram at your own by drawing by referring to this transition table, right? So the final state will be Q3, initial state is Q0. So when we draw the transition diagram, in that transition diagram, Q3 will be the final or accepting state, right? This transition diagram is okay. This transition diagram is okay. This transition diagram is okay. You can draw the transition table, sorry, transition diagram based on this transition table, because this transition table is okay for the given problem, right? This is the summary which we can see. Now we jump to next question number 6. Describe a finite automata and list its component as a 5-tuple, which I have explained. The same question has been asked repeatedly, right? So answer will be same. As you can see, answer will be the same. We have already discussed this problem, this question, solution of this question already. Now we jump to next question, that is question number 7. Construct a DFA for the language of all strings over 0, 1 that start and end with the same symbol. That start and end with the same symbol. As you can see, we are starting with the same symbol 0 here and ending with the same symbol 0 in state Q3 and Q4. So Q3 and Q4 are the set of final states or accepting states. Q0 is the initial state or the starting state because it has been marked by arrow, and double circle indicate these are accepting or final states. So the input symbols are 0 and 1. You can draw this transition diagram by referring to this transition diagram, and I have explained the logic. When we apply the 0 symbol on state Q0, we get the next state Q1. When we apply 0 on Q1, we get the state Q0. Right? So this is the question number 7. That is the required DFA. Deterministic finite automata, I have already explained to you. When we apply some input symbol on any state, we get only one output state or one next state only. But in NFA, we get the multiple states. We can get the multiple next states, right? So this is the explanation, right? If you at some stage, if you are finding some transition diagram, some problem with transition diagram, you can refer to the given transition table. As you can see, this transition table is again okay, right? Based on the transition table, you can draw the desired transition diagram, right? Now we go to the next question, that is question number 8. That is, design a automata which accept the entire set of strings over input alphabet sigma AB, that is input symbols are AB, ending with BB. So question number 8, ending with BB. So this is the summary of the previous question, and this transition table, half of the part is shown in the next page. You can see here. So here the transition table gets completed, right? This is a summary of the previous question. So question number 8, we have to design a automata which accept the entire set of string over input alphabet sigma, where A and B are input symbols, that should end with BB. All strings ending with BB. So you can see Q2 is the final state, and here we are having the transition B. So B, and again we are applying A B here. So see the hovering of the mouse, this B and this B, right? Again this B. So ending with BB. So this is the transition diagram for the given question. Again, if you are finding some inaccuracy in this transition diagram, you can refer to the this transition table. Based on this transition table, you can draw your correct transition diagram. However, the transition diagram I think is okay for this question, right? So this is the transition diagram. So transition table based on this transition table. So you might be knowing that based on the transition table, you can easily draw the transition diagram, right? Now we jump to next question. That is, so this is the summary for the given question. Now we jump to question number 9. That is, question number 9 says, describe the components of a question number 9. Describe the components of a finite automata using its formal 5-tuple representation. So this question is being repeated third time. Answer will remain same. That is we have already explained, already done, right? Now we jump to question number 10. That is, we have to design a automata which accept the entire set of strings over input alphabet sigma, A and B are input symbol, containing B's in multiples of 3. Containing B's in multiples of 3. So here in this transition diagram, you can see Q0 is the initial state because arrow, it has been shown with arrow, and it is also double circle. So Q0 is the initial state as well as the final state. So in the problem, it has been given containing B is in multiple of 3. So we start from initial state Q0, we apply B, we get state Q1, we again apply B, we get state Q2, we again apply B on Q2, and we get the same state Q0 as the final state. So it is multiple of 3. B's are multiple of 3. 1B, 2B, 3B. Then again 4B, 5B, and then 6B. So multiple of 3. We are after reaching the final state Q0 from initial state Q0 itself, we are getting number of B's multiple of 3, as you can see. And complete transition diagram, because why we are applying A on Q1, because we have to draw all the possibilities. So when we are in state Q1, when we are applying A on Q1, we are getting the same state Q1 as the next state. When we are applying A on Q2, we are getting the same next state Q2. We are getting the next state same as Q2, right? So this is a complete transition diagram for the given problem. So based on this transition diagram, you can draw this transition table also. This is the transition table. So it is vice versa. If you know the correct transition table, you get draw the correct transition diagram. If the correct transition diagram is known to you, you can draw the correct transition table, right? So vice versa is true. So here the all the string examples have been given here. So the strings which are, you can see in the here, there are 3 B's, so it multiple of 3. This column represent the accepted string, this column represent the rejected strings. So if there are 3 B's, so multiple of 3. If there are no B's, that is zeros, 0 is also a multiple of 3. In this case, B A B B. So in this also number of B's are 3. In this case, A B A B A. In this case, so you can correct it. The number of B should be multiple of 3. So this is also rejected string. So let me highlight with red color. This is not the set of accepted string because number of B's are not multiple of 3. However, the transition diagram and transition tables are okay. So the answer is you can give the answer correctly by drawing this transition diagram and the transition table itself, right? Now we jump to question number 11. Question number 11 says that design an NFA, that is non-deterministic finite automata, for strings over A, B, that is A and B are input symbols that have AA as a substring. So AA should occur as a substring. Question number 11. AA as a substring. So Q0 is the final. Q0 is the start state or initial state because it has been marked with a single arrow, and Q2 is the final state because double circle. It is a double circle, right? So when we start from initial state Q0, we are getting what? A. So if you are applying this transition, so A B whatsoever, A B B, but this A and the part of the string is, that is the substring is A when we reach the final state Q2. So A, you can again apply here A B A whatsoever, because A comma B means there are you can apply A and B any number of times. This A comma B means you can apply A and B any number of times. Same is the case here, right? But when we reach the final state Q2, starting from initial state Q0, we get the A as the substring. So this is the required transition diagram or required solution for the given problem, right? So question number 11 has been solved, right? Now we jump to question number 12. Question number 12 says that explain the process of eliminating epsilon moves from an epsilon non-deterministic finite automata using an example. So how to eliminate or remove epsilon moves from an Epsilon-NFA? Clear? So this is the transition diagram. You can see on the left side we are having an epsilon example, Epsilon-NFA, and on the right hand side you can see easily we have removed all the epsilon transitions, right? So there is a procedure. I will be explaining that procedure. Based on that procedure, you can easily eliminate the epsilon moves from a given epsilon non-deterministic finite automata. That is, you can easily remove epsilon moves from given Epsilon-NFA. So let me explain the concept. An Epsilon-NFA allows transitions on epsilon. That is, when we apply some epsilon symbol, we get the next state we take a transition from input state to next state, meaning the automata can move between states without consuming any input symbol. So there is epsilon means there is no input. It is not equivalent to any input symbol. There is no input symbol. So to convert it into an equivalent NFA without epsilon mode, that is without means by removing the epsilon modes, we use the epsilon closure method. So this epsilon closure method has been explained for your convenience step by step. First step says that in the first step, we have to compute the epsilon closure. That is for each state Q, we have to find all the states reachable from Q. So please notice when we using zero or more epsilon transitions, that is we start from a state Q and we apply the epsilon as a symbol, and we have to find all the state reachable from this state Q, right? And the step number two states that we have to update the transitions for every state Q and input symbol A. Find all the state reachable from epsilon closure on input A. That is, we have to find all the states uh, on epsilon closure on input A. When we have determined this set of states in the first step, then we have also need to obtain all state reachable from epsilon closure Q on input A, right? Then take the epsilon closure of all those reachable state again. That is, what do you mean by this statement? That is, again, we have to apply this first step, right? So this becomes the new transition for Q on input A, right? Then we have to update the final state. That is, a state Q becomes a final state in the new NFA if epsilon closure contains any of the original epsilon NFA's final state. For example, for your convenience, see, consider this epsilon NFA. This is the transition table for the given epsilon NFA. How do you know that this is a epsilon NFA? Because when we apply epsilon symbol, when we apply this epsilon symbol on Q0, we get the state Q2, right? So first of all, we have to apply the epsilon closure. How will we be obtaining? So epsilon closure of Q0 is Q2. Sorry, Q0 as well as Q2. Why Q0 Q2? Because when we apply epsilon on Q0, we get Q2. That's why this Q2, right? And also why Q0 also? Because epsilon means not any symbol. So that is null transition. You can say epsilon null. You can say so. You can apply epsilon on when we apply epsilon on Q0. We can also get the same state Q0 because epsilon is a null. That is epsilon null, right? Similarly, when we apply epsilon Q1, when we apply epsilon on Q1, there is no state, but we get the same state also as I explained in the first part. So when we apply epsilon on Q1, we get the same state Q1. Similarly, on when we apply Q2, epsilon on Q2, so epsilon closure of Q2 will be Q2 itself, right? Now, new transitions after removing epsilon moves. Now we are in a position to remove these epsilon moves. How? See, so when we apply A on Q0, we get what? We get Q1, and we also have to write the Q2 because epsilon closure of Q0 contain Q2 also, right? So in this manner, again see how to determine this new transition table by after removing epsilon moves. Start with the initial state Q0. When we apply this A symbol on Q0, we get next state Q1. That's why this Q1. Also, we get Q2 because epsilon closure of Q0 also contains Q2, right? Now, when we apply B on, sorry, let me explain this removal of epsilon move step again. Let us see the step. So we have to update the transitions for every state Q and input symbol A. Find all the state reachable from epsilon closure Q. Okay. What does it mean? So epsilon closure of Q0 is what? Epsilon closure of Q0 is Q0 Q2. So now we have to apply the symbol A on Q0 and as well as Q2. So apply. When we apply A on Q0, we are getting Q1, right? When we are applying input symbol A on Q0, we are getting Q1. That's why this Q1 next state, right? And when we are applying A on Q2, when we are applying A on Q2, we are getting nothing. But because epsilon closure of Q2 is what? Epsilon closure of Q2 is itself Q2. That's why the Q2 state is included here, right? Next, now we'll be calculating when we apply B on Q1. So what is the epsilon closure of Q1? That is Q1. So apply B on Q1. So when we apply B on Q1, we get the state Q2. That's why this state Q2, right? Now, when we apply A or B on Q2, we are not getting. What is the epsilon closure of Q2? It is Q2. So when we apply A and B on Q2, we are getting nothing. So that's why these are empty. So this is how do we update the transitions. So I hope you have understood this concept. You can read this step number 2, how to update the transitions, right? First of all, you have to obtain in step number 1, you have to obtain epsilon closure. After obtaining epsilon closure, you have to apply the symbol on all these epsilon closure. First, we apply A on Q0, Q2, then B. Then we apply A and B on Q1. Then we apply A and B on Q2. That is on all the epsilon closures. So in this manner, you can remove the epsilon moves from Epsilon-NFA. So if next time the same question appears, I will not be explaining the same steps again, because we have dealt with the solution of this problem by explaining to you all the steps in ultra detail. So I will not be explaining the same question again. Right. Now the next question, you can see the summary here. Now we jump to the next question, that is the question number 13. Question number 13 says that define epsilon NFA and explain how it differs from NFA. So difference is simple. In epsilon NFA there are epsilon moves, and in NFA there are no epsilon moves. So comparison you can see here. So in standard NFA or non-deterministic finite automata, there are no epsilon moves. As you can see, there is no epsilon. There is no transition on applying any epsilon symbol. So this is the standard NFA. And second is the epsilon NFA, where when we apply some epsilon on some input state, we get the next state. For example, when we apply epsilon on S0, we are getting S1. When we are applying epsilon on S0, we are getting S2 also. When we are applying epsilon on S2, we are getting the final state S3. So this is the epsilon NFA. So what are the key differences? An epsilon NFA includes spontaneous transitions on the empty string. As I have explained, epsilon means null or empty. Specifically, this epsilon means empty, allowing state changes without consuming any input. So there is no input symbol A or B. Epsilon means empty. Standard NFA only permit transitions on the input symbols from the input alphabet. So this adds another level of non-determinism. Note the concept of epsilon closure. Epsilon closure of what will be the epsilon closure of S0? So step number 1, which we have dealt with in the previous problem. What will be the step? Where epsilon closure of S0 will be S0 itself also. So when we apply epsilon on, because epsilon means empty. So when we apply as empty epsilon on S0, we get the next state as S0 also. And we in this transition diagram, you can see when we apply epsilon on S0, we are getting S1 also. When we apply epsilon on S0, we are getting S2 also. So this is how to compute the epsilon closure of a particular state. So this is the first step while removing the epsilon moves from a epsilon NFA. This is the first step, as you can see here. This is the first step. First step says that we have to compute the epsilon closure for all of the states in the input alphabet. When we compute, after that, we have to update the transitions based on this set of rules. That is, how will you update transitions? First of all, we have to consider these epsilon closures. And once you consider the epsilon closure, for example, epsilon closure of Q0 is Q0, Q2. So starting state will be Q0, right? Right? And we apply A and B on Q0 as well as Q2. Then we get these next states, right? Similarly, when the input state is Q1, so we look at the epsilon closure Q1 and we apply A and B on Q1, right? Similarly, when the next state is Q2, we focus on epsilon closure of Q2. What is the epsilon closure of Q2? Q2. So we apply Q2, we apply A and B on Q2, and we get the next state. And where to see this? By referring to the given transition table, right? This is how we can remove the epsilon moves from epsilon NFA. Now we move to question number 14, which says that design a automata which accept the entire set of strings over input alphabet A and B are input symbol containing A is multiple of 2. So now the A should be in multiple of 2. So as you can see, uh, this is Q0 is the starting or initial state as well as the accepting or final state, because arrow indicates it is a starting or initial state, double circle indicates it is a accepting or final state as well, right? Now, this is all. Please consider this as a single transition. This is not a double transition. By mistake, this is a double transition shown here. This is only a single transition like this, right? This is only a single transition. We apply when we apply A on Q1, we get the next state as Q0, right? So but containing A is in multiple of 2. So we start from here. So this arrow means, this loop means we can apply B any number of times. Then we apply A, we get the next state Q1. Then again we apply A. So starting from Q0, again we are reaching Q0 on the final state. How many number of A's are there? A, 1A, and then two number of A's now become 2. Next time when you apply next A, that is 3A. Then again A. So after reaching final state Q0, how many number of A's are there? 4. 4 is a multiple of 2 again. Next, this cycle goes on. Again A, that is 5th A, this 6th A. So again reaching on the final state Q0, number of A's are 6. That is again a multiple of 2. So this is the transition diagram for the given question, right? I hope you have understood the answer. Now we jump to question number 15. Question number 15. So question number 15 says that draw the transition diagram for DFA accepting all strings with an even number of 0 and even number of 1. So on reaching the final state, you should have the even number of 0 and even number of 1. So here also Q0 is the starting or initial state because it is marked with arrow symbol, this arrow, right? And it is also marked with double circle, so it is also the accepting or final state as well. So when we start from starting state Q0, 1, then we apply 0, so then we apply 1, then we apply 0. So after reaching again final state Q0, how many number of 1s and 0 are there? 1, 1. So there are two number of 1s. 0, this 0. Let me show you. This one and this one. So number of 1s are 2. Again, we apply 0, 0. So number of zeros are 2. So number of 1s are 2, number of zeros are 2. So how many? So number of 1s are even and number of zeros are also even. And this cycle goes on. When we again repeat this cycle, number of 1 will become 4 and number of 0 will become 4. So that is also even. Now the vice versa. Now we start from Q0 state. Now we consider these. Now we consider this 0, right? This 0, 0, then 1, then 0, and then 1, right? Again, this 0 and this 0, green 0. Number of 0 are again 2. Number of 1 are again 2. So again we are getting number of 0 and number of 1s as even. And this cycle goes on. So this cycle goes on. Please see the mouse hovering of the mouse. This cycle goes on. And always when we reach the final state Q0, starting from the initial state Q0, we get the even number of 0 and 1. Right? I hope the question has been clear to you. Solution has been clear. You have got the solution right. Now we jump to question number 16. Design a regular expression for strings over AB that begin with AB and end with BA. So strings should begin with AB and end with BA. So as you can see here, this is Q accept is the final state because it is marked with double circle, and Q0 is the starting state because it had been marked with arrow. So as you can see, here when we start from Q0 and we apply A, then we apply B. So we are starting with AB, and after that we apply here loop means you can apply any number of times the symbol B, and also when we apply A, B, then A, we reach the final state Q accept. So it is starting with AB and ending with BA. Actually, this transition diagram is trying to explain to you that when we start from initial state Q0 and we reach to the final state Q accept, then The strings are starting with AB and ending with BA. Remaining transitions are shown because those possibilities can also be there in the complete transition diagram. So I think there is no need to explain the uh, transition diagram. Now you are enough expertise. You are having enough expertise to solve the given problem to draw the given transition diagram. So this is the required DFA, that is deterministic finite automata, right? But in this question, we have been asked, we have to design a regular expression, not the DFA. After drawing the DFA, the regular expression will be this. The regular expression will be this. This is the required regular expression for the given problem. As you can see here also. How? You can see, you can derive this regular expression from the transition diagram itself. For example, A, B, when we start from Q0, A, B, then A, this is the final state, then plus means or. Then again we start from initial state Q0, A, B, then A plus B. A plus B means you can apply this, either A or B. So here A, we get the final state, that is Q accept, and B again. So either A or B, and the asterisk. This asterisk means that zero or more than zero number of transitions. Basically, there are two signs. One is asterisk, one other is plus. So asterisk symbol means there are zero or more than zero, and applying the input symbols, and zero or more than zero occurrences. The plus means one or more, right? So A plus B means plus means A or B, and star means by applying A or B zero or more than zero number of times, right? So this is the desired regular expression. Then we apply what? Then we, how come this BA? This transition B, and then again A. Again we are reaching to the final state. So this is how we can obtain this, the desired regular expression, right? So successfully we have solved this problem also. Now we jump to question number 17. Question number 17 says that distinguish between NDFA and DFA. We have already done this question. So already done. Now we jump to question number 18. Question number 18 says that convert the following NDFA to DFA. So how to convert this NDFA to DFA? See, NDFA to DFA. So this is the given given NDFA to us, that is non-deterministic finite automata. How to derive the DFA from it? So let me explain. This is the required answer in the form of transition diagram, but let me explain the steps. So see, first of all, we start from the initial state, right? We start from the initial state Q0. Q0 is the, it has been given in the given problem, Q0 with arrow. So arrow means it is the starting or initial state. Star means Q2 is the final state, right? It has been given in the problem. Now, how to convert this? You can see how you come to know that this is a NFA, because when we apply the symbol 1, input symbol 1 on a state Q0, on an input state Q0, we are getting multiple states as the next state, or next multiple state as the output states Q0 and Q1. That's why it is an NFA, right? As I already explained to you. Now, how to derive a DFA from it? It is very simple. What you have to do, first of all, when we apply 0 on Q0, we get Q0, okay? And when we apply 1 on Q0, we get Q0, Q1. So now we take this Q0, Q1 as a single combined state as the input state, right? As you can see in this transition diagram also, Q0, Q1. This Q0, Q1 now has been considered as a single combined state. What we have to do? We have to again apply 0 and 1 input symbol on this state. How will you do? How will you apply 1 on Q0 and Q1 combined? When, how? See, first of all, we take state one by one. We apply first, see the input symbol 0. When we apply 0 on it, when we have to see in this transition table, when we apply 0 to Q0, we get Q0 as the state, and when we apply 1 to Q0, we get the Q0, Q1. So just a minute. When we apply, sorry, yes, when we apply 0 to Q0, when we apply 0 to Q0, what is the next state? Q0. When we apply 0 to Q1, because Q1 we have to apply, na? When we applying 0 to Q1, we are getting what? Q2. So we'll be moving to a combined state Q0, Q2. So we are going, when we applying 0 to this 0 to Q0, Q1, we are getting what? Q0, Q2. As you can see here, Q0, Q2. Bus. This is the basic idea or concept behind converting a given NDFA to DFA. We have to uh, follow the same procedure. Now we get the another state, new state. So this will become the next input state. Again, we have to apply 0 on this and 1 also on this. Okay. When we apply on 0, transition has been given to us. When we apply 1 on Q0, we are getting Q0, Q1, right? So, this transition has not been shown. Let me show you. This is the 0 transition, okay? But this is the 1 transition. This is the transition for applying the input symbol 1. How? Let me explain to you. So Q0, Q2 will become the now the input state. Now we apply first. We have to apply 1 on Q0, Q2. How will you apply? First you apply 1 to Q0. What you are getting? On applying 1 to Q0, we are getting Q0, Q1. That's why Q0, Q1. And when we apply 1 to Q2, we are getting nothing. So we are getting nothing. So that's why after applying 1 to Q0, Q2, we get the next state as Q0, Q1, right? So in this manner, we can convert the given NDFA to a desired DFA. And next time such type of problem will come, I will not be explaining, but I will show you the solution directly, because we are not having the enough time, because we have to solve 75 number of questions, right? Again, if you are the steps are not clear to however I have explained to you, you can refer to these steps at your own, right? You can refer to these steps at your own to find the desired DFA. However, the same steps have been explained to you by me, right? So see, uh, whatever we are getting, we take those states become the input state. So when we apply 1 on Q0, the next state is Q0, Q1. So this Q0, Q1 now becomes the new input state, as you can see here. This becomes the new input state. Similarly, Q0, Q2, when we apply 0 on Q0, Q1, we get the next state Q0, Q2. So Q0, Q2 also becomes the input state, new input state. Similarly, we are also getting a new state Q0, Q1, Q2, Q0, Q1, Q2. So this also becomes the new input state. So what you have to do, how to get this, how to get this. So when we apply 0 on this Q0, Q1, Q2, so first of all, you have to separate. First of all, you have to apply 0 on Q0. Then we have to check the next state. We have to write the next state here. Then we have to apply 0 on Q1. We get the next state. We have to write next state here. Then you have to apply 0 on Q2. We get the next state. We have to write this next state here. So in this manner, this is very simple if you follow the steps. So this is the summary. Now we are trying to solve the question number 19. Question number 19 says that differentiate between Moore and Mealy machines with an example illustrating their outputs. Question number 19. So we have to differentiate between Moore and Mealy machine with an example illustrating their output. So these are the some of the key differences between Moore and Mealy machine. As far as output dependency is concerned, Moore machine is output in case of Moore machine is dependent, or it is a function of present state only. But output in Mealy machine is a function of present state as well as input. That is, in case of Mealy machine, output depends on present state as well as input. As far as state count is concerned, in case of Moore machine, number of states, Moore machine requires more states, whereas Mealy machine requires fewer states. As far as the response speed is concerned, Moore machine is slower, that is output changes on clock edge. Mealy machine is quite faster and output can change between clock edges. As far as stability or glitches are concerned, Moore machine is glitch free, Mealy machine is prone to glitches. State diagram notation is concerned, in case of Moore machine, output within the state circle. In case of Mealy machine, output on the transition arrow. So these are the differences, and these are the examples of Moore and Mealy machine. I'll be explaining. So as you can see, this is the example for Moore machine. So here we in Moore machine we have to write the state / input symbol also, right? So when we apply, I will be explaining how to uh, draw the Moore and Mealy machine and the conversion process between Moore to Mealy and Mealy to Moore later on. So in that time you will get the situation clear, right? So to understand the differences between Moore and Mealy machine, it helps to first understand they are both types of finite state machine. Think of finite state machine as a simple brain for digital system that decides what to do based on its current state and what is happening right now, that is input. So you can this is the same differences I have explained earlier. You can refer to these differences at your own by reading at your own. So these are the key differences in the form of a table, and this is the example for one complement generator. So you can draw the Moore machine as well as Mealy machine for the one complement generator, right? So in case of Moore machine, since Moore output depends on states, in case of Moore machine, output depends on state only. As I have earlier told you, in Moore machine, output depends only on the present state, whereas in Mealy machine, output depends on present state as well as input. So it produces an initial output even before receiving input. So it does not depend on input. Moore machine does not depend on input. Output only depends on the current state in case of Moore machine. It does not depend on input. So in this manner, I will be explaining to you. So this is an example for a one complement generator. You can refer to this example later on when I will make you understand how to draw this Moore and Mealy machine for the given problem, right? So you can refer to the solution later on. Now let us move to very important question of minimizing the automata. So question number 20 says that explain the step-by-step procedure for minimizing a automata or minimizing a deterministic finite automata with a sample automata or example, right? So this is the given automata to, for example, as an example, let us consider this DFA, and after considering this DFA, we have to minimize this automata, right? So there are some steps. There is a method called partitioning method for minimizing an automata. So minimizing an automata or minimizing a DFA means reducing the number of states. Minimizing means we have to reduce the number of states to the absolute minimum required as far as we can, while still accepting exactly the same set of string. So the when we reduce the number of state, but we still accept the same strings, right? So think of it as cleaning up a logic diagram to make it as efficient as possible. So there is a method behind minimizing the automata called partitioning method. So first step is remove the unreachable states. So these are the steps. Please listen carefully because these are the only steps based on which you can minimize the automata. So step number 1 says that remove the unreachable states. So those states which are unreachable, we have to remove them. Clear? To those states we cannot reach from starting state. Those states can be, you can say, dead states. We have to remove those unreachable states in the step number 1. So before starting, look at the given DFA. Is there any state that you simply cannot get to starting from Q0? It means starting from Q0, is there any state we cannot reach to? We can also reach to Q5, we can reach to Q1, Q2, Q3, we can also reach to Q4. There is no state, right? But in this case, we have been given in this diagram, we can reach Q1, Q2. Okay, we have to remove those states which cannot be reached directly. For example, starting from initial state Q0, we can reach to directly to Q1, either to Q1, Q2, Q5, but we cannot reach to Q3 and Q4 directly. So Q3 and Q4 are unreachable states. That's why we will remove these states from the given DFA. So these two states are removed, Q3 and Q4, because starting from initial state Q0, we are not able to reach Q3 and Q4 directly from Q0. That's why we will remove these unreachable states Q3 and Q4 from the given uh, uh, DFA, right? So this is the first step, right? Now we go to the step number 2, which says that create the initial partition P0. Now how to create the partition? We start by splitting all the states into two piles or groups. We will divide the given states into two groups. So group A will be non-accepting state, right? Non-accepting means non-final states. And group B will contain accepting state, that is final state. What are the final states? Final state is only Q4, right? So the group of final state will contain a partition that is containing only the state Q4. That is Q4 is the final state, and remaining state will be putting or keeping in the other group. As you can see in group A, those are not non-final. So you can see what are the non-final state: Q0, Q1, Q2, Q5, Q3. All these are non-final states or non-accepting states. Clear? Step number 2 is this. Now, there is a rule which states that states in different groups can never be merged. So, because there are two groups, the states in these two groups can never be merged. You have to remember, right? Now, refine the partition P1. We have to define the first partition. So, we are getting here two partitions A and B. We have to first define the first partition P1. So now we look at each group and see if the states inside it behave the same way. To behave the same for every possible input 0 or 1, they must land in the same group. What does it mean? Please listen carefully. If we apply input symbol, what are the input symbols? 0 and 1. So if we apply 0, for example, 0 on Q0, what we are getting? If we are getting the next state which lies in this group A, so right, so that is okay. So as you can see, uh, first of all, we have to compare. For example, group A contains states Q0, Q1, Q2, Q3, Q5, right? So we will be comparing all pair of states within group A first. We will compare two states, right? In group A, every pair of two states in group A, right? For example, we take Q1 and Q2, right? So we apply 0 on Q1 and also apply 0 on Q2. And we have to check we are getting the next state. For example, when we applied the input symbol 0 on Q1, we are getting Q3. So Q3 is present in group A, right? It is okay. When we applying 0 on Q2, we are getting again Q3. Q3 is also present in the same group. So same means the next states are in the same group. It is okay. So it means they are behaving the same way. Q1 and Q2 are behaving the same way. Now when we apply 1, we have to check both. If one of is not same, then it means that those states are not behaving same, right? So when we apply 1 on Q1, next state is Q4, right? You can check from this the given DFA, right? When we are applying 0 on Q0, we are getting Q1. When we are applying 1 on Q0, we are getting Q2. This is the given DFA, where you can check what is the next state, right? So when we applying 1 to Q1, you are getting Q4. So Q4 is lying in this. Okay. Okay. Next state is Q4. So Q4 is also lying in the same group, na? When we applying 1 on Q2, again we get Q4. So Q4 is lying in the same group, na? So it should not be such that one next state is lying in this group and one state is lying in this group. So in that case, they will not be behaving in the same way. We will set this clearly, right? Now we'll be comparing all of these pair of states in a similar fashion. We take next states Q1 and Q3, like right. So here I can show you Q1 and Q3 are Q1 and Q2 are equivalent, we have found. But Q1 and Q3 are not equivalent. Why? Because when we apply 0 on Q1, we are getting Q3. So Q3 is lying in group A, whereas when we apply 0 on Q3, we get Q4. Q4 lying in group B. So next state Q3 is lying in group A, and because Q4 next state is lying in group B, because they land in different groups for the same input, when we applied the same input 0 on both states Q1 and Q3, that's why they are not equivalent. But Q1 and Q2 are equivalent, but Q1 and Q3 are not equivalent, right? So this is how to refine the partition P1. I think you have understood, right? So you have to check for every pair of states. So the our new refined group of P1 might look like this. So you can see we have not taken Q1, Q3. In this group, we have not taken Q1, Q3 because these are not equivalent. Q1 and Q3 are not equivalent. That's why we have eliminated Q1 and Q3 group, right? So the next state of groups will be, as you can see, Q1, Q2 we have included because they are equivalent. Q1, Q2 is one of the group. Similarly, right? So these are the groups formed. Then we have to repeat until no more changes occur, right? When we are not able to divide more further groups, we can stop there, and these will be the final set of states. So in this manner, this will be the final because we cannot divide the groups further. We get when we are trying to follow the same procedure again, we get the same groups again, same groups again. So this is the now the you can say the desired states in the minimized automata. As you can see in the diagram, let me show you in the diagram. Diagram is drawn. So Q0, Q1, Q2. As you can see, Q0, because Q0 is the initial state, you have to keep it as it is. What are the remaining groups? What are the remaining groups? Let us see. What is the first group? What is the first group? Q0, Q5. So you can see Q0, Q5 here. Just a minute. Just a minute. Let me take. Let me. Okay. 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 Just a minute. Okay. Let us see whether this desired automata has been drawn for the same given DFA or not. So let us proceed further. Draw the minimized DFA. Finally, you combine the states that stayed in the same group into one single super state. For example, Q1, Q2 are stayed together. Q1, Q2. So Q1, Q2 are stayed together. So that's why we consider them as a single state, right? Q1 comma Q2, because they are lying in the same group. Any arrow that used to go to Q1 or Q2 now just goes to this new merge state. So whenever you apply 0 on Q1 or Q2, if we are getting only Q1, then also the next state will be Q1, Q2, right? You can see this, you can read this statement, right? Now summary of the concept. Summary, we do not need to go. Logical breakdown. So breakdown for the diagram. Now we have to draw the minimized automata. So state Q5 at the bottom is unreachable from the start Q0 or part of separate logic loop that does not reach the final state. In standard minimization, it is discarded. So do not need to include the Q5. Why? This okay. Uh, Unreachable state say that state Q5 at the bottom is unreachable from the starting state Q0. Okay, so this is true. From starting state Q0, from starting state Q0 in the given DFA, we are not able to reach Q5. Let us read it again. So it says that state Q5 at the bottom is unreachable from the start state Q0, but it is reachable. And next it is saying, or the part of a separate logic group that does not reach the final state. Okay. because it is not part, it does not reach the final state, so it is discarded. Okay, so that's Q5 is discarded. That's why the whole state Q0 Q5 is discarded. Okay, so what we are left with, we are left with Q0 initial state, and then Q1 Q2. Okay, then Q1 Q2, this group 2, and Q3, and these two groups, group 3 and group 4, Q3 Q4, Q3 Q3 and Q4, right? And Q4 is the final state will remain the same as in the given DFA. Final state will remain the same. So as the Q4 is the double circle, it will remain the final state. Why we have discarded the Q5? However, why we have discarded this entire group this group 1 Q0 Q5, because it consists of a state Q5. However, the state Q5 is reachable from state Q0, but uh, when we are going to reach the final state Q4, uh, Q5 is not getting in between. We are not using any, we are not following any path following on to the final state Q4 where the Q5 comes in between. That's why we have also discarded Q4, Q0, Q5. This group 1, Q0, Q5. So the remaining states in the minimized automata will be the starting or initial state Q0 and these three remaining groups. And these three remaining and these three remaining and these three remaining groups. Right? One Q0 starting state. Just a minute. One state will be in the minimized automata, one state will be the starting state Q0, and the remaining three states will be Q1, Q2, Q3, Q4. One more thing, which I have already explained. When you are applying 0 or 1 on Q1, Q2, right? When you are applying, for example, you are applying 0 on Q1, Q2. In this case, only because we are getting the state Q3, there is no problem. In this case, also when we are applying 1 on Q1, Q2, we are getting a single state. So suppose in place, this is the correct transition diagram for the minimized automata. Suppose I am trying to explain you. Suppose perhaps this state might be, for example, let it be Q3, Q5. Let for an example, and you when you apply 0 on Q1 and 0 on Q2, you are getting Q5. So still there, because when you are applying 0 on Q1 and 0 on Q2, you are getting Q5. Still in this case, you will be getting a transition from this state, right? On applying 0. I have already explained this concept. I think you have got the uh, idea, right? Okay. So this is the minimized automata, and one I have now explained all the steps how to draw the minimized automata from the given DFA. I will not be explaining the remaining different questions or different problems of the type that is to determine the minimized automata from the given DFA. Steps will remain same, only the given DFA will change. So I will not be repeating the same concept or idea. I will not be solving again the same problem of different given DFA. That is how to get the minimized DFA from the given DFA, right? Now we go to question number 21. Construct a Mealy machine. Construct a Mealy machine that outputs 1 when the number of ones in the input so far is even. So output should be 1 when the number of even is even, right? Just a minute, I have a phone. I have to attend a phone call. Just a minute. हेलो हाँ जी मैडम आपने मुझे व्हाट्सएप किया ना मैं चेक कर लेता हूँ मैडम सर मैडम मैंने नहीं 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 सर नहीं मैडम मैंने जिला मैडम को कंप्लीट कर दिया था टाइम चेंज हो गया था ना कि पोस्टपोन हो गया पेपर 26 को हो गया था तो इवेंट हमारा 25 से 30 अप्रैल ना होगा 25 से 2 मई हो गया था तो सॉरी 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 25 अप्रैल लिखा हुआ है 27 हो गया 27 से 2 मई हो गया तो मैंने दिव्या को बताया था, मैं एक बार देख लेता हूँ कि ये वही पोस्टर के लिए है। हाँ, पहले मैं इनका नाम देखता हूँ। यस 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 यस, मैं आपको, हाँ मैं, नहीं 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 नहीं, परहैप्स ये वही होगा, तो आप काइंडली काइंडली ये डेट चेंज करवा देना। हाँ मैं देख, हाँ हाँ जी मैं चल रहा, हाँ जी ठीक है। हेलो, हाँ जी मैडम वही है इसमें डेट, हाँ जी डेट चेंज करवा देना। हाँ जी 27 अप्रैल से 2 मई तक। ओके थैंक यू मैडम। ओके थैंक यू मैडम। So now I am resuming. So question number 21 says that construct a Mealy machine that outputs 1. So the output should be 1 and the number of ones should be even. Right? You have to draw the Mealy machine. So as you can say, this is the Mealy machine. Now let me explain you to the steps. Clear? So you can see, check Mealy machine. I have told you that the output depends on present state as well as input. Right? In Mealy machine, output depends on present state. So here you can see Q0 is the starting or initial state because it has been shown with arrow. And in Mealy machine, output depends on present state and input. So what is the present state? Q0. What is the input applying? You are applying so the number of ones are even. Okay. Ones are even. But in this final state has not been drawn. Let me see the other example of Mealy machine. So I'll be explaining this problem number 21 later on when we'll be explaining the steps of drawing the Mealy machine. Right? I'll be explaining later on question number 21. I have remembered this question number 21 I'll be explaining this how to draw the Mealy machine. But you have to but you have to remember the basic difference between Moore and Mealy machine. That is, in case of Moore machine, the output depends on output depends only on the present state, but in Mealy machine, output depends on present state as well as input. Right. So these are the inputs. Right. So I'll be explaining later on when we'll be dealing with the steps in detail. Right. So because the steps are not shown here, you will not be able to understand. So let us jump to question number 22. Distinguish between Mealy and Moore machine. The answer to this problem has already been explained to you. Further, you can refer to this solution also. Right? Already done. We have already seen the differences between Mealy and Moore machine. Right? These are the steps of also. What is this? Question number. Okay. Question number 22. We have already seen. That is the differences between already done. 22 question already done. That is difference between Moore and Mealy machine. Now we jump to question number 23. that is convert the following NDFA to DFA. I will not be explaining this problem because such type of problem I have already explained to you. How to convert NDFA to DFA, right? However, you can refer to this solution to get the desired result. So this is the given original NDFA given to us, and this is the equivalent DFA that we have got by the steps following, which we have already done in the previous problems, right? Now we jump to question number 24. Differentiate between Mealy and Murray machine with respect to how outputs are produced. How the outputs are produced in Mealy and Murray machine. That is question number 24. That is again the difference between Mealy and Murray machine. So now we go to question number 25. Construct a Murray machine that output 1 when the number of 1 in the input so far is even. So earlier we were asked the same problem, but in that case we were supposed to draw the Mealy machine. In this case, we need to draw the Murray machine. So in this case, this is the Murray machine. So let me draw the Murray machine. So in the given problem, we have to draw the Murray machine. First of all, remember in Murray machine, output depends only on the present state, right? So here you can see Q0 is marked with the arrow sign. So this is the starting or initial state. So Q0 represents an even number of ones. So when we start from Q0 and we again going to the same state Q0, we are getting the same state again. So number of ones are even. When we start from Q0, apply 1, we get Q1. Apply 1 again on Q1, we get the same state Q0. So number of ones are even in this case. Same case in Mealy also. Now I'm going to explain the question number 21 also. So see, as we start from, so Q0 is also the, when we start from initial state, starting state Q0, this is the Mealy machine. Q0, starting state, we are applying 1. This is the input symbol. This is the input symbol, right? So we reach Q1, right? So this slash, before slash is the input symbol. Okay. So again, we are applying 1 here. So we get to the same state Q0. So the number of ones are even here, right? So the in case of Mealy machine output, what is the output? It should output 1. What was the problem? Problem number 21. It should output 1 when the number of 1 are even. So you can see before the slash symbol, this is the input symbol. So 1, 1 before slash, this one and this one. When we apply 1 here, we start from Q0, we reach to state Q1 by applying 1 here, right? When we apply 1 on Q1, this one, we reach to Q0. So here number of ones are even, okay? And this is the output. After the slash, the output. So what is the output here after the number of ones are even? After the number of ones are even, what is the output? Output is 1, right? So this is the desired way to draw the Mealy machine. I hope you have understood the problem. Before the slash, we are applying the input symbol, and after the slash, we are having the output. Clear? So when we apply 1 on Q0, we get the next state Q1, but the output is 0. When we again apply 1, so we are reaching the same state Q0, but the number of ones are even, so the output is 1, right? So in this manner, you can draw the Mealy machine. So, but in Murray machine, the output depends on what? The output depends on the present state only. That's why the output has been written here /1 Q0/1, because in Murray machine output depends on only the present state. In Mealy machine, the output was after the slash symbol here on the transitions, right? So this is the basic difference. Why we are getting here output 0 Q1/0? Because only the number of ones after reaching Q1 from Q0 our number of ones are odd. So when we are applying 1 and again 1, number of ones are here even, and output is, that's why 1, right? So you have to remember. So this is how you can draw the Mealy and Murray machine for the given problems. Furthermore, later on we will see how to convert Mealy into Murray and Murray machine into Mealy machine. So there can be two types of questions can be asked. First question can be draw the Mealy or Murray machine. Second type question is Mealy to Moore conversion or Moore machine to Mealy conversion. So if the problem, same type of problem occurs, I will not be explaining again. Now we are in a position to draw the Mealy and Moore machine. Later on, we will see how to see the conversion. That is how to convert Mealy to Moore and Moore to Mealy. Right? So now we are going to discuss the question number 26. Describe the limitations of question number 26. Question number 26. Describe the limitations of the pumping lemma for proving non-regular languages. See, what describe the, because pumping lemma is meant for only proving regular languages. Now we have to describe the limitations of pumping lemma for proving non-regular languages. So pumping lemma is a useful tool for proving that certain languages are not regular, but it has important limitations. Okay, pumping lemma is used for proving non-regular languages. Sorry, pumping lemma Pumping lemma is a useful tool for proving that certain languages are not regular, but it has some limitations. What are the limitations? It is only a necessary condition for regularity, not a sufficient one. So this means some non-regular languages may still satisfy the lemma, and the lemma cannot prove that a language is regular. So what are the key limitations of the pumping lemma? First limitation is only a necessary condition. All regular languages must satisfy the pumping lemma. However, not all non-regular languages fail it. Some non-regular languages can still meet the lemma's conditions, so the lemma cannot detect all non-regular languages. Second limitation is it cannot prove regularity. That is, if a language satisfies the pumping lemma, it does not guarantee that the language is regular. Example is certain non-regular languages may accidentally satisfy the lemma's pumping lemma property. So the let me see the video is going on or not. Let me see whether the video is going on or not because the stop sign is not showing.